So let's now go deeper into this start, stop, and the main complication will be in compute, right? Because that is where the chunk of the T steps lies. So start is simple. So this is a Boolean formula that asserts the start configuration. Which is SC1 variable. This has to be Q of S and the pointers or the two heads should be at the beginning. And input tape should have X and U, because both X and U is the combined input. And finally, work tape should be empty. Right. So these are the conditions, and we are doing an AND over them. That asserts the start configuration. Similarly, stop. So this will assert, it's a Boolean formula that captures or asserts that M stops and outputs 1. So which means that the state should be stop. So finish state, and work tape header should come back to the original position, and we don't care where the input tape head is. And work tape should have the except the 1 bit at the end. Well, at the end, or we actually can be more concrete and just say that just demand that 1 is at the beginning. Okay, so again this state is finish state. Work tape head has come to the beginning and has put a 1 in the beginning. Okay, so it has basically cleared the work tape and just put the output. So these are the easy Boolean formulas. You can see that it's just an AND of equalities, and equalities you can implement quite easily, right, in terms of AND or not. So let me just show how. So A equal to B condition is implemented as either both A and B is true, or both are false. Right. So this, for example, implements that two variables are equal, either both are true or both are false. And yeah, the state variable can take as many values as the number of states, but that is finite and constant, right? It doesn't depend on input size, so you can actually do an you can check these things bit by bit, and using this this idea, this bit equality, you can implement also for other strings. So for bits, you can implement it like this. And then you can extend it to strings, equality of strings. Right, so with this, let us now move to compute. So what is compute supposed to do? So this will assert that there is a sequence of steps following the transition function. A configuration sequence G0 to Gt minus 1 of the Turing machine M starting from C1 and ending at C2. Right, so basically this talks about there exist G0 to Gt minus 1. So G0 is C1 and Gt minus 1 is C2, and for every I from 0 to t minus 1, I want to say that Gi to Gi plus 1 follows a valid transition step, where I means it is following some step given by the transition function of M. Okay, so this part is basically saying that configuration Gi to Gi plus 1 follows transition I given by delta. Now, transition function has only finitely many, it's a finite description, right? It's part of the finite control of the Turing machine. So, what this for all I part of the formula is saying is that Gi to Gi plus 1 is coming from exactly one command from the transition function given by I, and remember that number of i's is constant, it does not depend on n. So, number of i's is constant, right. Again, this, if you think about the definition of Turing machine, you will see that finite control does not really depend on the input, does not depend at all on the input. So this number of i's is constant, and hence this OR is actually, we are just writing down every element of the transition function. One of them will be followed by gi to gi plus 1, and then we are going over all the i's. So you just open this up t times. Okay, do an AND. So this is an AND of t things. AND of t formulas. Okay, so that is, those are the comments, and now what remains is yeah. So let me go back, talk about compute again. So compute has been broken into three parts. Starting from C1, which is G0, and C2, which is GT minus 1. There are these G0 to G1 transition and G1 to G2 dot dot GT minus 2 to GT minus 1. Right. So GT minus 2 to GT minus 1. All these steps have to follow, they follow some transition given by delta. Now this has to be implemented or checked by the Boolean formula step. So we have to go there now, define that, what is that? So in general, for two given configurations C3, C4, configurations, remember, are given by their this array. You can think of this array or the data, right? State, pointers, which is head positions, and the tape strings. Given this for C3 and for C4, and also given a transition I from this delta. All you have to check in step is, the Boolean formula has to check whether C3 to C4, can you go from C3 to C4 in one step using I. Okay, it's just a consistency check that you have to do. So you can reduce it to basically equality tests and AND over that. Okay, so this will be a bit painful, but let us anyways go through this. So what you want is, you want to assert that C3 to C4 transition or step follows the transition I, which is from on state as B1, B2 under the input head, respectively work tape head, you have B1, B2. So from there you go to state S prime. You can not change the input, but you can change the work tape, so make that B2 prime. And then what direction to move. So epsilon 1 for input tape, epsilon 2 for work tape. Right. So I, remember, is given to you when you are to define a step formula. I is given, and it is like this, these 7 values. And C3, C4 is also given, the arrays are given. Now you have to do the comparison. So let's do that, finish it. So for epsilon 1, epsilon 2, equal to, let's say, stay. Okay, that's one case. Let's do this case first. We use the formula. So this will be the state of C3 has to be S. Why? Well, because I needs to begin from S and go to S prime. So C3 has to have state S and C4 S prime, right? So we are just implementing that or expressing that. And then we have to now talk about the positions of the input and work tape heads. So they are, let's say, K prime and K. There exist these numbers such that let me use a different color for this. There exists K prime, K, such that P prime Cj, sorry, C3 is P prime C4 is K prime. That's because epsilon 1 is stay input tape, yeah. So input tape head should not move. So K prime doesn't change from C3 to C4. That's where the head is. And similar thing for work tape head. Okay, and now this transition I also tells you about what was under the heads, right? So that was B1, B2. So here we implemented that in the configuration C3, C4, the input tape head started with B2, ends with B2 prime. And what else does the transition want? It wants, B1 to not change. So A prime, K prime, C3 is B1, and rest of the input and work tape strings don't change. Okay, so this is the main implementation of checking whether a step was correctly followed or not. Right, this is the most local check you are doing. It's from one configuration to just the next following I. Right, so this I hope is clear. But I have implemented this only for stay. There are 3 other choices, right? In fact, many more choices are there because you can either stay, or you can stay, go right, stay, go left and go right, and so on and so forth. All these 9 possibilities are there. So similarly for other, or analogously for other analogous expression or formula for other epsilon 1, epsilon 2. Right, depending on what I was given to you to define a step I, you can write down such formulas and do the check for this given C3 to C4 whether it satisfies it. So this Boolean formula is true if and only if this C3 to C4 followed transition I. Right, that's what we have achieved. Now some things are still missing, or I should point out. So remarks So first point we have to note is that x is fixed, x is a fixed string because that was given to you in the input. But we'll take u as a formal variable. Why is that? Because remember what was our original goal? Our goal was to show that this problem L in NP can be reduced to SAT. So basically we want to express the verifier M computation as a formula with variables, right? So what will be the variables? The variables will be the certificate part. The U part will be the variables. So I should mention here that the idea with the unknown certificate. Okay, so the u we will keep as the variables. So semantics being that if u exists, then the formula will be satisfiable. I mean, or if the formula ultimately is satisfiable, then there is some u. So that becomes a certificate. Or if the formula is unsatisfiable, then the u doesn't exist. There is no certificate. So that will tell you whether x is in L or not. Right? That's the original plan. This I have already discussed, that equality on strings can be expressed as a formula in CNF, right? That was basically this thing that first do it for bits and then AND this over each and every bit of your two strings. So whenever I am using equality in the formulas, formula description, it can be implemented as CNF. That's not a problem. When I am using for all I operator, right, I use this for all I less than equal to t minus 2. So this can be expressed as ANDs, conjunction, right? You have basically for every I we have given some formula and then do it around t many times. Just copy it that many times. That is not a problem. And the most important thing which I'll not discuss here, will not work out here, is that how to write this there exists K, how to implement this as a CNF. There exists K prime K. This thing is tricky. Okay, because this remember K prime can take t values and same with K, so they are taking t square values. But there exists means that you have to take an OR disjunction, right? How do you write it as conjunction? So this needs a property of Turing machine, which you will see in the assignment. You will solve it. Well, also other issue is that not just the OR, but another issue is that K actually will depend on the input exact string X. X, U, and step I. But U we have not even fixed. U we are taking as a variable, right? So actually this is a bigger problem than just disjunction, because K really depends on what step you are at, step I. What is X? Well, that we can fix because X was fixed. That is still okay. But yes, I can remove X part, but U we have taken as a variable. So we want it to be a variable. So then K also becomes a variable, and then we cannot write this expression as CNF. Right. So we need a uniform way for K prime K to be defined. We should know it already. So the way it is done is assume that M is an oblivious Turing machine. That is, head positions only depends on size of X and I. Okay, so it actually in a way only depends on what is the step you are at, and you already know that function of n and I. You don't need U for it. Okay, oblivious machine doesn't need to know X comma U. So it's not X comma U. That is not needed. So what this means is that so K is known as a function of step I, and we do not need the and we can express there exists K as CNF. Okay, so this oblivious Turing machine conversion is true for any Turing machine, and it is without loss of generality. So you do solve this as an exercise. Okay, so we'll finish this reduction next time.